Is Romuald Janik, and he's going to tell us about rapid interactions at strong coupling.
Okay, so thank you very much. I would like to thank the organizer for giving me this opportunity to give this talk. So I would like to describe this talk mainly recent work done with Tomek Łukowski from Kraków on finite size effects in the giant magnum dispersion relation. But I would also like to describe some earlier work done together with Jan Abron and Charlotte on, let's say, relation of finite size corrections swapping interactions with TBA inspired formulas. So the plan of my talk is as follows. First, I would like to just briefly recall anomalous dimensions and ADS-CFT. So what is the problem, and what problem in this context I would like to address, from what particular point of view I would like to approach this. Then I would like to describe, the breakdown of the beta ansatz from two sides. From the side of gauge theory, namely from the spin chain point of view and Feynman graphs, and from the point of view of string worksheet, and show that, on both sides it's quite natural to expect that one has a breakdown of the beta ansatz point of view. Then I would like to give a brief review and give some examples of finite size corrections which have already been computed, both at strong and weak coupling, and then I would like to describe how one could derive a generalized Licher formulas to compute some of at least an example of these corrections quantitatively. Exactly, not only with not only the exponential term but also the full prefactor. And I will then use these formulas to give and show how the computation for the giant magnum goes on. So, of course, on the gauge theory side, we are interested in the scaling dimensions of operators, which can be defined because n equal to 4 is just an exact CFT. And in general, of course, these the dimensions behave in a quite complicated way as a function of the coupling. For the simplest Cornish operator, we have the one loop, two loop, three loop result, and we are waiting for the four loop result, which is extremely important, especially in this context. Now, in general, a lot is known about long operators, which are just composed from very many fields. However, so in this talk I would like to discuss complications which arise when L is finite, or at least it's not infinitely long, but what kind of, let's say, corrections appear when L is not strictly infinite or something like that. So now one can look at this question from 2 points of view. So first of all, from the gauge theory point of view, we would like to find all anomalous dimensions of all gauge theory operators as functions of the coupling. And on the string theory point of view, it's equivalent to quantizing the string, the redshift theory, redshift quantum field theory of the superstring in ADS5 process 5 theory. And of course, these are extremely difficult problems, but because we have integrability, we can try to address both of them. So now I'll just briefly review integrability on the gauge theory side, of course, but just to state some fact. So we have those celebrated BS equations, which here I wrote in a truncated form just to a single component, as it would appear, for example, in just a single subsector of the theory. So to solve for delta, we have to find the momenta, so we have to find the beta equations, solve the beta equations, which e to I pi L, where L is the length, which is the number of fields entering the operator. Here we have a product of the S matrices, which of course are known now currently, which depend on the coupling constant. And so once we solve those equations, we obtain the dimension from the formula that delta minus j is the sum of these celebrated square root-like type expressions with 1 plus 8 g squared sine squared pi over 2. Now these excitations are just magnons, and they have, of course, this non-standard dispersion relation. Of course, this is generalized to all possible operators in the Weisser-Stadacher asymptotic beta ansatz, plus numerous tests. But of course, it's not exact, and in fact, in the first paper of Bajsov-Dipper and Staudacher on the Bethe-Ansatz or loop Bethe-Ansatz equations in the SU2 subsector. Already, the authors explained, exactly what kinds of gauge theory interactions are not included and which are conjecturally included. So, if we want to compute the anomalous dimensions of operators, it's the same as computing a two-point function and looking at the behavior at large distance between the position of this operator and position of this operator. So here we have traces of operators which are put in those, represented by those dots. And generally we have Feynman graphs with a lot of propagators connecting those two. And now if the graph is in a way has a topology of this form, namely it's like a strip, then conjecturally the asymptotic Bethe-Ansatz equations of course include all those types of contributions. However, as BDS pointed out, we can also have at sufficiently higher loop order graphs where there's a propagator or propagators going all around the loop. And they claim that certainly, since these types of contributions are turned on at an order in the coupling constant which depends on the number of operators which form this number of fields which appear in a single trace operator, then certainly this type of corrections cannot be described using Bethe-Ansatz that they formulated. So it would seem that one would have some kind of breakdown of asymptotic Bethe-Ansatz in this case. So it raises, let's say, two questions. So one question of purely practical interest is, can we really compute those things? Because we would really like to know the spectrum of any root over super-Mills theory, and we would really like to solve the theory. So this would be filling this table of dimensions which Matthias showed in the first lecture to fill the other half of the table. But on the more, let's say, theoretical, from the more theoretical or aesthetical point of view, we would like to understand whether these type of open interactions, they violate the Bethe-Ansatz, but do they violate integrability? So whether one can really use integrability to compute them. So this would be the main goal, and I will just only touch on a bit. So it's the main open question. How to is integrability broken? And I would like to argue that in a way, no, that in fact they are very natural also in an integrable field theory or from an integrable point of view. But they seem to suggest that one needs to really introduce a different structure instead of the Bethe-Ansatz. So, and the main open question would be what structure one should introduce in the place of asymptotic Bethe-Ansatz. So this was the violation of asymptotic Bethe-Ansatz on the gauge theory side. Now, on the string theory side, what we have to do, we have a closed string in the planar theory, so it's just a cylinder, since we neglect all string interactions. Now the delta are just energy levels of an integrable quantum field theory which lives on the cylinder, because of course the cylinder is embedded in ADS5 and it gives this very complicated theory. However, now it's widely, since the first work of Benaposhilsky-Royban, one believes that this quantum field theory is really integrable. It's also, there are lots of indications that it's also integrable on the quantum level in various formalisms. So what is currently known? So we have some elementary excitations of this theory. Well, of course, here I would say that everything depends on what kind of gauge fixing one uses when quantizing the string. So using different gauge fixings would give perhaps different pictures. So all this is if we stay within the standard light cone gauge fixing for the string. In some covariant approaches, the picture will be completely different, but the physical results will be equivalent. So in this light cone quantization, one deals with elementary excitations which are, let's say, the magnons. They have a non-standard dispersion relation of the same form as before. Now it has not been, well, okay. So the main point here is that it's not a relativistic theory, of course, which is well known. And this is the main complication in studying this problem. Now, it is also known that these magnons scatter with a 2 by 2 S matrix, which has the following structure. So there's a matrix structure determined first by Niklas Byset, which is a product of two SU2/2 S matrices, or central extended ones, times a scalar function depending on both momenta, which is the dressing phase. Now, there's a conjecture which gives a complete form of this dressing phase for any value of the gauge coupling. Initially, it was known for at strong coupling, it was a leading piece by Eltonov for Stadacher. Then at one loop, it was the Hernandez-Lopez piece, and recently Stadacher and Byset-Hernandez-Lopez determined the remaining part which satisfies all the requirements. So in fact, it among the series of various solutions to the cosine equations of Byset-Hernandez-Lopez, BS picked the one particular case which is believed now to be the physical dressing phase of the ADS5 string S matrix. So now, these properties, since we are talking about the S matrix, are for the properties of this integrable field theory on a plane, on an infinite plane. Since in order to define the S matrix, you have to deal with asymptotic states, for example. So, but we are dealing really with a closed string, so we have to put the theory instead of a plane onto a cylinder of a certain size. And we want really to find the spectrum of the theory on the cylinder. So the first guess, for the spectrum would be a better ansatz quantization, which is derived from this S matrix for the magnons. So of course, because of this matrix structure, we are dealing with a big nested better ansatz equations, but schematically it's again of the same form as before. And the physical meaning of this better ansatz is of course that if we have a magnons, we take one of the magnons and take it all around the cylinder, then it gets a phase from here, and also it scatters with all the other magnons which form the same state. And of course the wave function has to be single valued, so the better equations follow. But now again, one can ask whether this is exact. In fact, it's not exact due to virtual corrections. And already one can see this picture, I mean, why it cannot be exact, from the point of view that the argument which leads to the better equations from single valuedness of the wave functions treats the regions just as if they would be quantum mechanical particles. But we really have a quantum field theory. So in what way, how one can see that it's not exact? So the simplest possible case would be just to consider a single excitation, a single magnon. Then the better equations are completely vacuous because we have just a single magnon, so it doesn't have any other thing to scatter on. So if we have a single excitation, we just get its dispersion relation. So now the question is the dispersion relation in fact exact? Of course, one may worry a bit that for the string we have always a level matching constraint, so the total momentum has to be 0. So a single magnon is not really a physical state of the string. But so either one can live, with this and impose total momentum level matching condition later, or we can just, for example, use the Oberfold theory, which was used by Semeno, Grignani, Forini, and for specific rational values of the momentum, the magnon is really a physical particle, and then in fact one could, apply this picture to real physical states, but not in equal to Fosse-Puyang-Mills theory, but to some restricted case. Okay, so what happens to the dispersion relation? Now, in fact, it has been known since 80s that in relativistic theories, the dispersion relation can get modified and will get modified. In fact, in particular, even the mass of the particle, if we compare the infinite volume mass to the mass of the particle in a cylinder, these two expressions will be different. And Richer, in 1983, derived universal formulas which give the leading corrections at large size of this picture. So they have the following form. First, it's the F-term correction. So it corresponds to the case where we have a magnon propagating on the cylinder, and we have a virtual particle, a virtual magnon which goes across along the cylinder. And they interact, and because of these interactions, this changes the self-energy, and of course it will then modify the mass of the particle. Another possibility is the mu term, namely the magnon would then, if there's a bound state in the theory, the magnon could split into two particles, which would then recombine, and also it would give a contribution to the self-energy. And this is the mu term. And Richer derived for relativistic quantum field theory exact expressions which are completely universal. Namely, the mass shift coming from this graph is given by a certain integral over the rapidity of this particle which goes in the loop. What is important here is that it is an exponent minus the mass times L times cos theta, which is the interpretation exponent minus L times the energy of the particle which goes along the loop. So this exponent in a way gives the magnitude of corrections which we can expect to appear. Now, a significant factor here is the forward infinite volume S matrix in the forward direction, evaluated as theta plus I pi over 2 with some complex shift of the rapidity. So I would like to argue later why this shift can be understood qualitatively very easily. Now, anyway, what's really important here is that the whole expression for the mass shift is completely determined by infinite volume data. So once we know the theory at infinite volume, I mean there's a unique prescription to find the leading corrections at finite volume. So this is the main point right here. There's also an analogous formula for the mu term, which in the simplest case when we have just a single particle species, which can be found from taking the residue of the S matrix at the pole, which would appear here. So ultimately, one would really like to have these similar formulas for the ADS5 cross S5 theory, but of course, in ADS5 cross S5, there's no relativistic invariance. So for example, the S matrix will no longer be a function of a single parameter, but will be an independent function of two momenta. So that's why one has to really generalize those formulas to this case, and this will be the main, point of our point of our work was to try to find a generalization of those formulas, which could be applied for the ADS5 cross S5. Okay, so this was the results for a single particle. Now, what would happen for multi-magnon states? So unfortunately, this is an extremely interesting question from the point of view of ADS5 cross S5, because multi-magnon states are really the physical states which would correspond to, for example, the Cornish operator. However, unfortunately, even in the relativistic case, no universal general formulas are known up till now, so it will be very interesting to find them. However, still one expects virtual corrections. For example, they can come from similar types of graphs as before, but of course there will be many more of them. For example, we have two magnons, and we can have a magnon which goes on in this loop. Now, from this point of view, one can see that these corrections will depend in a very complicated way on the types of constituents here. So, in fact, especially if one would go to higher orders, there will be a very complicated interaction between the constituents which appear here. So very probably, almost surely, one cannot really describe this type of modifications through a modification of the beta ansatz. So we cannot really hope to modify the S matrix to have some kind of effective S matrix at finite volume and use modified beta equations. But really we have to use a complete different framework to describe at least these results, at least if we want to get exact results, which would be valid also including higher order corrections. So despite the fact that I said there are no universal general formulas. However, for some specific integrable relativistic quantum field theories, one can get exact results for any L, and there are various approaches like thermodynamic Bethe-Ansatz, the Destry-de-Vega equations or nonlinear integral equations, and also functional relations of Bozanov-Lukan of Zamalchikov, which in a way encompass both of these approaches in a, let's say, a more abstract way. But in fact, from those relations, one can derive either this or this, depending on, as discussed by Patrick today. So the ultimate goal would be to find something like that for P 5. Okay, so to conclude this part, we see that the asymptotic Bethe-Ansatz is not exact on the gauge theory side due to open interactions for the in the Feynman diagram picture. From the redshift quantum field theory point of view of the string, we have virtual corrections, namely excitations which go along the cylinder and modify the Bethe-Ansatz quantization. So Etienne and Charlotte, we suggested that one should really identify perhaps roping and virtual corrections as being the manifestations of the same phenomena, but which is seen, I mean, here on the AD side and here on the spin chain side. Now, here I would perhaps like to comment that when one considers integrability, very often one can make manipulations either on the gauge theory side or on the redshift quantum field theory side. And some issues are much easier to see from the gauge theory side, and some properties are much easier to see from the redshift quantum field theory point of view. And some are quite similar. For example, the dispersion relation came explicitly from the spin chain point of view, where the discreteness was explicit, and only much later it was seen from the redshift quantum field theory of view, like Jagiellonski with the sign p over 2 appeared as the dispersion relation. For the S matrix, one can really translate arguments here to here verbatim using the Zamalchikov-Faddeev algebra. So really it's completely equivalent. However, I would like to argue that from this point of view of identifying roping interactions, it seems that it's much easier to look from the redshift quantum field theory point of view. Because from the gauge theory side, in a way the spin chain formalism does not give a hint how to proceed, because spin chain as it stands is exact at finite L. So in order to include roping interactions, we have to somehow supplement it by some dynamical assumptions. So for example, there was a very interesting idea of using Hubbard model here, but it seems that it's extremely difficult to extend it to the full PSU22/4 setting. However, if we stay within the redshift quantum field theory point of view of the string, it seems that in a way we see that just standard properties of quantum field theory tell us exactly at once that Bethe-Ansatz cannot be exact, because in any quantum field theory we always expect virtual corrections. So we know from the start that we have to have violations of Bethe-Ansatz. And moreover, like Lichev's formulas say that in principle, once we know the theory on the infinite plane, so we know the S matrix, this determines completely in a unique way how to calculate the leading correction for at finite size. So in principle, I mean, one would hope that knowledge of integrability at infinite length, infinite on the plane, could give the complete properties of the theory even at finite L. So consequently, would give a unique prescription of calculating roping interactions. So from here, it's quite interesting to see. Okay. Now I'll just give a brief review of some calculations which have been done where failures of the asymptotic Bethe-Ansatz have actually been seen. So the main point which I will contemplate later will be these finite size corrections to the Magnum dispersion relation, which were first found by Autonov and Zamaklar in these light cone gauges, and in the context of this orbifold theory, which I mentioned, where one can translate these corrections to some physical corrections for some operators in this orbifolded theory by Asolti, Forni, Vignani, and Semenov. So at infinity j, one has, of course, the dispersion relation of this form. And it's finally j and large lambda, one can look for the classical solution of a string which has a finite extent in J and calculate its energy for fixed coupling. And the result is that we have an exponential term of the form e to minus 2 pi j over square root of lambda sine p over 2 times some factor here which has specific dependence on momentum, on lambda, and a curious numerical factor. So I would like to argue that in fact this is quite easy to understand and generic, and then I would like to use Lichard's formulas to show how one can compute the whole answer here. Now there are also other calculations like exponential corrections to spinning strings. So if we take the spinning string, the classical solution, and then consider quadratic fluctuations about it, do a resummation of the 0-point energies, then one finds one piece which is consistent with better ansatz, and another piece which has e to minus 2 pi j over square root of lambda type of magnitude, which is goes beyond the better ansatz. So I would like just to argue later how one can see just this magnitude here, but for the moment we cannot really compute the per factor in this case, because here the spinning strings are really composite states of very many magnons. So this is really a very interesting open problem. And as we part of mentioned in the previous talk, there's a problem for twist 2 operators in the SL2 sector, where so this is extremely interesting because it's a weak coupling, so it's the only kind of, let's say, solid information that we have at weak coupling, where we have a breakdown of the better ansatz equations. Namely, there's an inconsistency with BFKL expectations at follow-up order, which is exactly the first order where open interactions should contribute. So this will be also extremely interesting to check, but also it's very difficult because these are multi-magnon states. So for the moment, so I will just stick to the context of a single magnon. And so first I would like to just describe a bit how can one understand the magnitudes of the corrections. So with Jan and Charlotte, we suggested that one could use this thermodynamic better ansatz approach to get a kind of intuition what will be the picture here. So the idea is that in thermodynamic better ansatz, at least for the ground state, it's much simpler to state, that we want to see, for example, how the ground state energy depends on the size of the cylinder. So to get the ground state energy, we can compute the partition function on a very large cylinder, take r to infinity. In Euclidean space, the asymptotic behavior at r going to infinity will be the ground state energy. But of course, it's extremely complicated because we have here the cylinder at finite size, so we have lots of virtual corrections, and we cannot really compute it. But the idea of TBA is to look at the same situation and take the Hamiltonian to be running in this direction. Now, we have to compute the partition function in this picture, which is the same quantity. But now the theory is defined on an infinite line, so there will be no virtual corrections because they are very highly suppressed. So here the better ansatz is exact for this theory. But since the time direction is compactified, we really have a thermal ensemble. But we can do a thermal statistical physics with better roots, and from here one gets TBA equations. And now I can interpret the outcome in this form and extract the ground state energy. So from this point of view, one sees that the basic features what one has to do is to do a space-time interchange, because we want to pass from this picture to this picture where there's no problem with virtual corrections. So this amounts to a double Wick rotation in both energy and momentum. So ETBA is minus I times the momentum, PTBA is minus I times the energy. Now, one can see that this interchange is implemented in relativistic theory very easily, namely theta goes to theta plus I pi over 2. And if you recall, this was exactly this complex shift of the rapidity which appeared in Licher's formulas. So from the point of view of TBA, it's extremely natural that one has this theta plus I pi over 2 in the formula for the Licher term. Now, unfortunately, we cannot really write the TBA for our case. So what we did in this paper was to extract the exponential magnitude of the correction. And the exponential magnitude of the correction would be E2 minus j, the size of the cylinder, times the energy in this picture, where we quantize, for the mirror theory. So now let's apply these heuristics to the case at hand. So we have to perform the space-time interchange in idealistic worldsheet theory. So we start from the energy dispersion relation for the magnon, and we have to perform space-time interchange, namely put E equal to I times PTBA, P equals to I times E. We put in here, we have an IP here, minus sinh squared, and now we have to calculate this mirror energy in terms of the momentum. And we get this quite complicated expression that E is 2 times arc sinh, 1 over 2 square root of 2g times 1 square root of 1 plus p squared. Of course, for relativistic theory, the space-time interchange is trivial, and one will get here also relativistic theory, relativistic dispersion relation. But in this case, we have this strange formula. So we estimate that the magnitude of corrections in the F term would be E2 minus 2 pi j times this E2 minus 2j times arc sinh of this expression. So now does it make sense? So let's look how it behaves at weak and strong coupling. So at weak coupling, we have this expression here. So we take g going to 0. When g goes to 0, the argument of arc sinh is very big, so this is essentially a log. In fact, a minus a log of g, since g is in the denominator. So putting this together, we see that we get this term behaves at weak coupling as g to the power 2 times j. And this is very natural because this is exactly the magnitude which is typical of open interactions. So this formula, in a way, gives the correct leading behavior at weak coupling. Now, if we look at strong coupling, so g goes to infinity. So now the argument of arc sinh is small, so we can treat it as a linear function, and we get this result. Now, since we want to see the magnitude of the correction, so the leading piece will come from the region where the momentum of this magnon, which is integrated, over which we integrate, is smallest. So when p is 0. So this gives the estimate e to minus j over square root of 2 times g. And if we use the formula which links g with Stroff's coupling, we get e to minus 2 pi j over square root of lambda. So this is exactly the type of corrections which appear for when summing quadratic fluctuations for spinning strings, for example. So this is quite very nice.
Including the 2 pi?
Yes, including the 2 pi. So the full numerical coefficient in the exponent comes out correctly. Now, if you recall that for the giant magnon, the exponential term had a different dependence. Namely, it was almost like before, e to minus 2 pi j over square root of lambda, but also in the denominator there was a sign of p over 2, which depended on the momentum of the magnon. And now it turns out that it's very natural that this type of exponential term comes from the mu term. So if you recall, the mu term diagram looks like that. You get a magnon, which then split into 2 particles, which then recombined. However, these 2 particles were, all the 3 particles were really on shell. So we have both momentum and energy conservation here in the mass shell condition. And in principle, it's impossible to satisfy all those constraints using real momenta. And in fact, generally, for relativistic theories, the momenta which, for those particles which live here only for a short time are in principle complex. In fact, for relativistic theories, the magnitude of this term always agrees with the formula that it's like e2 minus j times the imaginary part of PC of one of those complex momenta. So let us take this formula, which I will justify later in a more rigorous way, and thus solve the mass shell condition for those three particles, but now using the dispersion relation for the giant magnum. In fact, here, one of those particles could be just a BPS bound state. In fact, in the case at hand, when we have a magnum here, one of those particles will really be a BPS bound state. But so here, instead of one will have 4. But the whole calculation at this order in the coupling constant does not change. So to solve that, we solve perturbatively for the complex momentum at strong coupling, and we get that PC is P plus 2I over square root of lambda sine P over 2. So if we plug it into this formula, we get exactly the type of exponential correction to the giant magnum dispersion relation, with the sine P over 2 appearing here in the denominator.
Why does the particle should be on shell?
Sorry?
Why does the particle should be on shell with a virtual correction?
Well, so I will show it later when I will. So I will go to the Richard's formulas. So here it's a bit hand waving, but I will go to the derivation of the Richard formulas, and then one can see where it technically comes out. Okay, so in this way one can understand very easily this exponential part of the giant magnum. However, and what we would really like to do is understand the full expression. So also understand this part here. Now this was also intriguing because one could compute a similar type of expressions in the Hubbard model, which does not include, for example, the dressing phase. And there, one could see from that specific model of working interactions that one got exactly the same type of exponential factor times a quite a different function here, with different scaling on momentum and different dependence with square root of lambda. So it will be very interesting to get the whole result. Also, from the previous arguments, I showed that in fact this exponential term is extremely generic. So the only thing which was used was just pure kinematics. So the same type of term would appear for any theory which is square root of 1 plus AG squared sine P over 2 dispersion relation. And so in the prefactor one really have to have information on the dynamics of the theory. So now can we understand this prefactor? So in order to do that, well, the best thing would be to have TBAs, because then in principle one could use TBAs to get all solutions, corrections to all orders in J. But of course we do not have them. So what we tried to do was we tried to go back to the derivation of Lischel from 83 of those leading finite size corrections, and to see whether one can modify this derivation and obtain more general results which could be applied here. So this was what we did in this last paper with Tomek Łukowski. So we want to generalize Lischel's formulas for generic dispersion relation, which is of this form: E squared is equal to some function epsilon squared of P. For relativistic case, epsilon squared of P is just m squared plus P squared, while in this case it's 1 plus ADG squared sine squared P over 2. And here the basic idea is to, if you want to find how the energy changes, to see how the mass shell condition is changed when we go from the plane to the cylinder. So the mass shell condition can be always reconstructed from the poles of the S matrix. So one really wants to see how the manifold of the S matrix from the poles of the Green's function. Sorry. So what's interesting is the inverse of the Green's function, and to see where it has zeros. So we define self-energy in a similar manner as in relativistic theories, but now extracting explicitly the full piece of the dispersion relation here. So in this case, the self-energy should be 0 exactly on the classical on mass shell. And also we fix the residue as in the standard case, so the derivative of epsilon should be 0 on mass shell. Now, So this is, let's say, true for the plane. Now we put the theory on the cylinder, and generically the self-energy will be modified. So it will get corrections from finite size. So now plugging the modification here and looking how the zero changes, we can reconstruct the shift of the energy as a function of this sigma of 3 in this simple manner. So we see that we have to compute the change, the finite size corrections to the self-energy for theory on the cylinder. Now, what Lisher did, and it's extremely generic, so it can be applied without change here, is arguments how to relate the propagator on the cylinder of circumference L to the propagator on the plane. In a way, to get propagator on the cylinder, we just have to average Green's function for the plane over translations by L. Now, in momentum space, this averaging over translations is exactly the same as multiplying all propagators by factors e to I n L times the momentum times Q1. And now, again, what Lisher did was he noticed and proved in the relativistic case that the leading correction at finite size when L is large will come from, so in general, if one makes these modifications, the graphs will be extremely complicated. So there will be a lot of modifications all over the place. But Lisher noticed that the leading correction comes from graphs which there's just a single additional factor of this type, moreover with this n equal to plus or minus 1. So we just have to look at the graphs and just modify a single propagator in the graph.
This is not an exact propagator, right? This is not just quadratic. What do you mean by propagator? Propagator is one over Laplacian?
Well, yeah, well, here I want to use the exact ones with the sigma, in fact.
But the equation for exact propagator is not linear. So when you average over, doesn't it suggest that you should use some kind of linear equation for propagator?
No, so I'll show the graphs in the next slide.
Also, in general, full propagator includes pieces corresponding to wave function normalization as well, not just self-energy.
Right.
So there's more than one unknown function.
Well, yeah. I can just, I guess, truncate, amputate these graphs and regularize it in some way. Right. Yeah. So, in fact, yeah, it is one perhaps I would say like that. This will modify some multiplicative factors, right? But one does not really expect these factors to really change the pole structure.
Okay, it depends how you define self-energy. If you take it as an overall.
Yeah. Yeah. So at least, so then one can look at this type of graphs, which one particular distributable graphs, and then distribute modification of the Green's function somewhere. So here one would see, so here the blobs are just generic vertex functions which we assume to be exact, but we don't need the form, and these are just the full exact Green's functions in the plane. So, and we add those factors in those various places.
And do you include a sum over all possible states which can circulate in the loop?
Yes, 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 yes.
So all possible bound states?
Yes, yes, yes. So this should be used here, indeed. So all these graphs look generally like that we have an integral over d to q over the two-dimensional momentum of these particles times the integrand which comes from those expressions. And now the idea for sure is the following, that to get the leading contribution, one can shift the contour of the momentum to imaginary values. So in this way, So if we shift Q1 to negative imaginary values, from the shifted contour, we'll get exponentially suppressed terms because it will be e to minus I times some kappa L. So we can forget about this result. So the shifted contour will contribute as a subleading term. However, when we shift the contour, we can very easily hit poles of the integrand here. And in fact, we will certainly hit poles coming from the Green's function here, which appeared g of q. So if we pick a pole of the Green's function, this means that the particle here has to be on shell. So we have this expression, which is the Euclidean version of the dispersion relation. And from that, we can compute that the momentum, Q1, is minus I2 arcsinch of this factor. So it's exactly the space-time interchange that I discussed earlier. And the factor E2 minus IQ1L becomes exactly this TBA-inspired exponential factor which I described earlier. So now, after this stage, instead of these two integrals, we have just an integral of a single parameter for an on-shell particle. So we have an integral over dq, E2 minus L e TBAQ, times something. And now, let's look at this something here. So one of the graphs was like that, and here we put this particle on shell. So in a way, this means that in the integrand, we can treat this expression not as a 2-point function, but as a 4-point function with on-shell external states. And in fact, if one does it for all expressions, one can see that all those graphs sum themselves together to the S matrix of the theory, infinite volume. And if one takes into account some residues, kinematical factors due to the different dispersion relation, one gets, at the end of the day, an integral over the single momentum of the particle, some Jacobian coming from normalization of the S matrix with respect to the Green's function, exponential factor here, and the contribution of the S matrix for those two on-shell particles. Now, so this is exactly the equivalent of the F term of Licher, but for the generic dispersion relation. Now, of course, also with this shift of the contours, one could very well also hit a pole of the S matrix, which appeared here. So, in fact, if that happens, one has to separately.
So, sorry, what are you equating to the S matrix in the diagrammatic expression above?
It's the fourth Green's function.
Thing on the right-hand side.
So this will be a sum of those terms and two other terms which come from those other
all
diagrams.
contributions to the S matrix look like a single S-channel exchange, maybe.
No, but from those terms here, if you cut this up and this up, there will be two terms. And then the sum of the two terms together will only be like that. So
the whole thing.
Yes. So all these graphs become the two different parts which contribute to the S matrix.
If you have the same argument for each one, put each one in shell.
Yes, and this happens to be so. So well, with one of them, one has to make a slight shift of the argument, but it's possible to do. So so in addition to this F term, if we have a pole here and we cross it, we have to add an additional contribution coming from the residue of this expression. So this will be like that, and this will be exactly the mu term, but now generalized to the generic kinematics. So we have those two kinematical factors, this expression evaluated at the position of the pole times the residue of the forward S matrix at the pole. So now we wanted to apply these formulas. In fact, we applied the formula for the mu term in order to compare with the calculation of Gleb, Sergei, and Maria. So we just look at this mu term. So first of all, we have to look at the forward S matrix and see if there are poles. So we did the computation for the magnum in the SU2 sector, at strong coupling. So of course there are those VPS bound state poles as found by Doyle. And one can compute the position of the pole. If the magnum has real momentum P, then Q star turns out to be imaginary, and in fact it's minus I over square root of 2G sine P over 2. So now if we plug this position of the pole to this E minus IQ star L, then in fact we exactly recover this exponential factor, which I argue to be far from this mu term. So in this way, it's much more rigorous and comes out.
So double poles of the S matrix don't contribute in this argument?
Yes, yeah, they shouldn't. Yeah. So now, what is the structure of the mu term? We have this kinematical factor. So if we plug in all the values here, we get just sine squared P over 2. From the exponent, we have the correct exponential factor e2 minus 2 pi L over square root of lambda sine P over 2. And the difficult part, or the remaining part, which is we have to evaluate the residue of the S matrix at the position of this bound state pole. So now, what is the structure of the S matrix? So it looks as follows. So we have the matrix part, which is relatively simple in the sense that the expression fit on one page. And we have the scalar factors which come from the dressing phase. Unfortunately, the pole just sits in this S matrix part, in the matrix part, and not here. So we have to compute the residue of this part and multiply it by the value of the dressing phase on the position of the pole.
What about the other pole corresponding to T-channel exchange?
Yeah, it was not included here. I don't know what will be the contribution. So, yeah. Right, so here it's not completely clear to me. I mean, in the course of how much one should shift, I mean, the contour.
Yeah, it depends on the
Yes,
contour.
yes. So, what is the natural choice of the shift? I mean, whether one can arrange that the BPS pole is behind and the one is left outside. So, that's also related to this issue of physical sheet, and so it's very interesting to really, indeed, look at it. Sorry? Because it's outside, it's after.
Is it also the case that sometimes you have simple poles which are not bound states, at least the heavier particles? Coleman,
Yes.
Thundercloud.
Yes.
Come on.
Well, but I guess here one does not have those poles. At least, this channel pole.
I don't know if you count
Which is-
T-channel exchange of a bound state as opposed to S-channel exchanges.
Looking at this for a heavier particle.
Yeah, they sit right on. That doesn't happen, or if it does happen, it's right on top of this other.
So, so here the residue of the matrix part can be computed, and in fact it turns out to be crucial to take the phase factor in the string frame from the work of Gleb, Sergei and Maria. Because if we now look at the contribution of the dressing of the AFS part of the dressing phase at the value of the pole, we'll get here exactly a phase factor which cancels with that one. So in the end we get a real answer. Yeah. And from here we have so there's one comment that if one would stop here, the G dependence and momentum dependence would be exactly the same as in the Hubbard model, which does not include dressing factor. And we see that the dressing factor, namely the leading AFS piece, modifies crucially both the coupling dependence and the momentum dependence. Here. Now the Hernandez-Lopez part will give just 1/2 at strong coupling. So at this stage, what we have is the following expression, putting all the expressions together. So we have G squared of 2 sine cube P over 2 times the exponential part times the contribution of the BS BHL phase, which we did not compute so far. Well, the classical string computation gives this result, so everything agrees, and we would like to have this part to be equal to 8 over E squared. So now we have to evaluate the BS BHL phase at the position of the bound state pole. in the strong coupling limit. So initially it's a bit puzzling because the dressing factor is really an expansion in powers of g. So the AFS has the form e to the g times something, Hernandez Lopez of the 1, and all BES BHL is suppressed in powers, inverse powers of g. So naively one would expect that this should not contribute at strong coupling in the limit that we compute. But however, it turns out that all those terms here are singular in such a way that they compensate for this factor of g. So all even orders of this BS BHL phase contribute here. So I will show now some formulas that these are very complicated expressions. So in this case, the BS BHL phase is an expansion. Here it's written in terms of 3 functions because of the fact that we evaluated at the portion of the BS pole, one of them is 0 by definition. One of the 4 functions is 0. All those functions are double series of this type, with the coefficients being given by these expressions with gamma functions, zeta functions, and various powers. And if we look, so this series can be resummed for, let's say, for n up to 14. One can get really, so these expressions are really some rational functions. And we can look that we always have a structure like that we have 1 over g to the n minus 1 times 1 over 1 minus xy n minus 1. And exactly at the BPS pole, this becomes 1 over g, so these factors compensate. Yeah. These factors compensate, and one gets a non-zero value, which is just some pure number. And in fact, one can extract this number for any n. It turns out to be 0 for odd powers, for odd n, while all even terms contribute. And the contribution of the BS BHL phase becomes an infinite series of this form, these are just numbers which are defined in such a way. So we have some powers, factorials, and zeta functions for even arguments. So now when we wanted to evaluate it, we find that unfortunately the series is completely divergent. So initially we found just a couple of first terms, found that they decrease, approach the numerical value which we would like them to have, but then they start to rise. So, but because of this feature that it decreases and only then starts to rise, it looks like an asymptotic series. So we use Borel summation. And since we have here exact analytical expressions for those for the elements of this series for n, we can really do it analytically. And the Borel summation traded this asymptotic series for an integral over t. And now we can evaluate it, and we find that it's 8 over e squared. So exactly.
Fully Borel resemble. There are no poles in the
Sorry?
transform plane. The series is there's no ambiguity when you do that. All the choices are confident.
No, no. Yes. So here it is from z using the standard procedure one gets z, and this is convergent. So there are no subtractions which have to be done. And in fact, so in this way we produce exactly this result, which is very nice. Then we looked at general A gauges, because light cone quantization can be done for a family of gauges, namely when on the string we take j plus a, the density of j plus a times e to be constant for any real a. And up till now I considered a equal to 0 case. And in fact, Autonov and Zamaclar computed the correction for any a, and the a dependence was given by an additional factor e2 minus ap cotangent p over 2 here. So wanted to see if we can get it also. So first of all, one has to make 2 modifications. The S matrix for non-zero a is related to the S matrix for 0a by this factor, which at strong coupling exactly gives e2 minus ap cotangent p over 2 times an additional factor e2 to the 2a. However, in those gauges, one has to remember that the length of the string worksheet is no longer equal to j, but is j plus a times the energy, epsilon of p. So we have to, in the exponential part, we have to put in this definition here. So we get the exponential factor that we want, and the factor e2 minus 2a, which exactly cancels this leftover piece. So we recover the correct a dependence here. Okay, now there's some questions, so and I'll go to the conclusions. So here to get the result, we used a Borel summation of this BS-BHL phase at strong coupling. However, there are a couple of very interesting proposals which are just given as convergent expressions for finite j, starting from the one in the BS paper, also by Ivan Didna and Volin, and also Dojhoff and Malsena. So it will be the question will be, do these really give the same results? Namely, and perhaps one can have a test for possible non-perturbative terms, which would, because all these expressions are derived in a way, it's not really clear. The series at infinity at strong coupling is not convergent. So now there's an ambiguity if there are some additional non-perturbative terms or not. So perhaps it would be very interesting to try to connect that and to use this result as a test for the presence or absence of those non-perturbative terms. But in fact, it seems to be very difficult. So in fact, initially we started to use those, but we failed, so we went to the strong coupling expansion. But it will be extremely interesting question. Okay, so now I will just summarize. So some comments that these were completely different computations. Namely, the computation of A over Z was just a classical string computation for a classical string embedded in ADS5 cos S5 space. While here we used generalization formulas and used the BS-BHL phase, which from the string point of view has the interpretation that it's just multi-loop string quantum worksheet quantum corrections. And we had really to make a Borel summation of all loop string quantum corrections to recover this classical piece. So this is really a very non-trivial consistency check of the BS-BHL proposal, given the extremely complicated formulas that arise there. However, it's really a test of the even part, namely the odd part, just for the kinematics somehow vanishes. So we cannot really test the odd part of the BS-BHL phase here. But I don't have a reason why it's not so. Okay, so now there are of course lots of open questions that one would like to answer. So first of all, it would be really interesting to apply this formalism to other cases. For the case of multi-Magnus states or physical states, this will be really the one of the questions. Perhaps Timo will hear about it from now. And ultimately, one would really like to have some kind of TBA or nonlinear integral equation which would describe the whole spectrum at finite j. So this would be really the moment. But we are still very far away, I guess. So thank you.
Questions? Matthias?
So you say, you did the Borel resummation, but then in this paper by Basso, Jagiellonski, they found that the scaling function is not Borel summable. Do you have some comment on this?
Well, so here we did the Borel summation, but just for the dressing phase evaluated at the BPS bound state power. So for that point, for this kinematical point, it's Borel summable because we could do it. But away from this point, I don't know because the expressions are so complicated.
So you don't see all the terms here, right? These odd terms.
So I don't see the odd terms at all.
So then those are.
I think those cause problems because here. Yes. So here it turns out that from the odd terms, also one has this type of cancellation here, but the value here comes out to be 0. I don't have any reason for that, but we checked it, and it happens like that. So here just the even part and also evaluated at a specific point, which would turn out to be Borel summable.
Okay.
So for a one Magnon case, this A dependence of the correction was very mild.
basically the main correction was still given by e to the minus j divided by this denominator. So that basically means that there were no dependence on the length of string for one Magnon case. It was determined by j. So if you have many Magnons, do you expect that the situation would be different and the correction would be given by the length by e plus j for the system, or it would be still given just by the value of j?
I guess probably by e plus j, I would say, by the length, because for example here, I mean also in this case, that is what was necessary in the other gauges, the L which we had to put in this formula was really this modified j plus epsilon plus the energy. So I guess that this would hold also.
So you expect that EP would be replaced by the energy, by the total energy?
Well, perhaps, but of course there may be subtleties because we do not really have formulas for the multi-Magnon case. So it's also that's the reason why they are.
If this would be the case, then you could use beta ansatz to study any basically operators, any lone operator.
Sorry?
If this would be the case, then the asymptotic beta ansatz would be possible to use to study any lone operator, well, not even lone, any heavy state,
Yes.
including these two operators, right? Because you just use the light cone gauge,
Yes.
and then the effective length would be equal to j plus e. The energy is huge, and there is no trouble at all.
I mean, perhaps, but I'm guessing. I cannot answer. I mean,
And
for
then
sure.
it would be able to get actually exact results, not just log s, by using the asymptotic beta ansatz. Do you think it is really possible?
Well, I must say that I don't know. I guess just from this argument, it would seem that the size will be set by the, let's say, explicit length in the gauge in which one would compute. Of course, the fact that the result should be the same, independent of the gauge, would mean that there should be some. If this would be true, there should be some very fine cancellation between the corrections. I mean, in a equal to 0 gauge with respect to a equal to 1 gauge. But really, to answer that, I would say that one would really have to have an example. I mean, with two Magnons, let's say, and the formulas for them, because then one could really have physical states and be able to play this game.
Are you working on that?
Sorry?
Are you working on that?
Well,
To Magnon case, I mean.
it'd be nice to guess, but I think Joe will talk tomorrow. I don't know.
Okay.
Okay, let's thank Romuald again. I'm only doing class for a couple of those.